Okay, welcome everybody. It's a great pleasure to welcome back Arnab Sen, Professor Arnab Sen from IACS Kolkata. Arnab, of course, did his PhD here in DTP under Kedar Damle, and then he went on to Boston to work with Anderson. After that, he went on to work in MPIT here in Dresden with Roderick Posner and others. And then he has come back and joined the faculty of Indian Association for Cultivation of Science and he has been there for quite some time there. Arnab has very broad ranging interest. And today is going to talk about one aspect of his research, which is aspects of thermalization in kinetically constrained model. So,
thanks, Rasdeep. And okay, let me just see if I get this out. Yep. Thanks, Rasdeep, for the introduction, and I'm very happy to be back in EIFR. It's nice to see that almost nothing has changed, including the canteen food. So,
cheers.
Yeah. That's why I said almost. Yeah. Okay, good. So today I'll discuss a bit about some interesting physics in kinetically constrained models. There are many open questions in this area, and I'd like to point some to you all during this colloquium, and maybe some of you will feel excited to think more about these kinds of issues. So needless to say, if something is unclear, please feel free to just stop me and ask questions. Okay. So before I begin the proper physics talk, let me, of course, acknowledge my collaborators. And many people would be familiar to you from this picture. So, for example, Deeptiman Krishnendu, Devashish is also here in the audience. And I would especially like to acknowledge the younger people in our group. And Shoram Nandi, Harshkar, Indrajit, they were former graduate students. Annesha was a postdoc in our group, and now they have moved to other places. And Moinak is a current graduate student in our group. Okay? So, good. So now let's go to the physics aspect of the talk. So basically, this talk is about thermalization of certain interesting quantum models. So, of course, we know that thermalization of macroscopic systems is completely ubiquitous. So, if you start with some non-equilibrium state and you just let it go, then basically, if nothing extremely strange happens, then it finds a unique equilibrium state, and different non-equilibrium states go to the same unique equilibrium state, and then you cannot distinguish them macroscopically beyond a certain relaxation. Okay. Good. So in this talk, we are concerned about something slightly different. I was just looking at the more recent talks in the DTP colloquium calendar, and you must have heard something similar in at least the introductory thing in Sanjay Moudgalya's lectures. So here we are interested in self-thermalization in isolated quantum systems. So the simple setting that I want to think about is that you have a theory on a lattice. That's what these grid points are supposed to indicate. And there is some Hamiltonian through which these degrees of freedom are interacting with each other. And that Hamiltonian is local in real space. And you start with some simple initial state. It may be completely unentangled, or it may be weakly entangled with some area law entanglement. And then you just let the system evolve, the wave function evolve under the action of the interacting Hamiltonian. Okay. So then you ask whether this thing self-thermalizes. Of course, if you look at the full wave function, full many-body wave function, because this is unitary dynamics, of course, it stays a pure wave function. But if you look at operators which are localized in space, like this patch is supposed to indicate, if you look at temporal evolution of such operators, that's what this schematic figure on the right is supposed to indicate, then if you start with different initial conditions which have the same average energy, and of course you can start with lots of initial conditions which have the same average energy, then beyond a certain relaxation time, which is order 1 for most systems, here order 1 means that it just does not scale with the size of the system. Order 1 could be a large number here or a small number here. In this context, it just means it doesn't scale with the size of the system beyond a point. Beyond this relaxation time, if you look at local properties, one seems to see that basically the memory of the initial conditions is lost, and the answer just depends on the average energy density of your starting state. Okay. So in particular, if you look at some eigenstate of this theory, which is at the same energy density, of course, because it's an eigenstate, this operator O would not evolve there, but that has to coincide with the thermal answer. Okay, so that brings us to something which again most of you might be familiar of, which is this eigenstate thermalization hypothesis. So essentially, the memory that the theory in some way has to self-thermalize, which just essentially means that for an interacting theory, if you consider a local patch, then the rest of the system should provide an effective heat bath for this patch. This thing should somehow be encoded at the level of eigenstates of the interacting theory. And there are very precise statements which one can make to that effect. And these can also be numerically tested. Unfortunately, in many cases, there's no analytic proof, but okay, there are several things one knows nonetheless. For example, if you resolve the dynamics like this in the eigenbasis, right, then basically you can make a statement about the expectation value of these local operators, which live here, in the eigenbasis itself, in the energy eigenbasis itself. And then you can make certain precise statements like this that typically, so by the way, these are statistical statements. Okay, so there can be violations of these statements, but these violations become increasingly rare as you increase your system size. Okay, so that's one thing to keep in mind. But okay, it's like random matrix theory also, right? You just put the thing on the computer and you can see that there can be outliers to the statement, but it's just that the number becomes extremely small as you increase the dimensionality of the system. Okay, so the point here is that suppose you look at diagonal matrix elements like this, which just means that this energy eigenvector is the same as that energy eigenvector, then basically it's extremely close to the thermal answer at that energy. So this epsilon is supposed to indicate that. And similarly, if you look at the norm of the off-diagonal matrix elements, it's again bounded by some very small number. And this very small number, according to ETH, goes like this, exponential of minus s by 2, where this s is actually the entropy at that energy density, right? So you can therefore see that this thing scales as 1 by square root d, where d is your Hilbert space dimension, right? So this kind of a scaling may be familiar to you from random matrix theory as well. Okay, good.
So this expectation of thermalization, how does this it's somehow in my mind and probably understood it, is it in conflict with this KAM theorem that tells you that there is a certain range around zero coupling where things stay civilized. How do these things?
Okay, so as far as I understand, if you take a integrable limit and then you go out of that integrable limit, if your system size is really big, in a quantum theory, there's really, as far as we understand, no KM basin. It just goes non-integrable. There is a long time scale here that you need to wait before you see the correct chaotic behavior. And that long time scale is controlled by how close you are to this integrable. But ultimately, it becomes chaotic. That's the current understanding.
And so this is the thing that is important here is that there are many degrees of freedom, or that it's quantum. Which one was keep on?
Like both. So because if you take actually, okay, let me backtrack. In fact, even classically, if you take a system which has many degrees of freedom, It's not known whether there's a finite basin for this reaction. So probably the more important thing is the many degrees of freedom. Yeah. Any other questions? Again, as I said, feel free to stop. Good. So in this talk, we are actually concerned with models with constrained Hilbert spaces. So we are actually all very familiar with constrained Hilbert spaces in our day-to-day research. So what does this word mean? It just basically means that suppose you have a spin theory, like lots of spin half degrees of freedom. Normally, when you build your Hilbert space, what you do is you take some state, maybe all up, then you flip a spin, that gives you another state, maybe then you flip some more spins and so on, right? So you can keep independently flipping your spins and just build all the states of your Hilbert space. In theories which have a constrained Hilbert space, there are some extra rules so that you cannot flip your spins independently. That's all. So in condensed matter, such theories naturally emerge in several interesting cases as low energy effective theories for problems with unconstrained spaces. So if you focus at low temperature, the right theory to look at is a theory with a constrained Hilbert space. So just to give an example, and I particularly like this example. Okay, sorry, this lattice is a bit complicated, but the physics is not so complicated. All of you know what a tetrahedron is. So take a tetrahedron like this and build a regular lattice of corner sharing tetrahedron. Okay, then the unique lattice structure that you get out of that is called the pyrochlore lattice. Good. Now, on each point here, you put a spin half degree of freedom and you write a xxz Hamiltonian out of these spin half degrees of freedom. So this is the Z coupling. I have written it in a slightly unusual way. I'll come to that. And this is the usual Sx plus Sy coupling written in terms of Lagrange. Now you go to a limit where this coupling in the Z direction is much larger than this particular coupling. That's all. So why have I written it like this? So this symbol just means that you go to each tetrahedron and sum up the 4 SZ operators there. So if you just sum them up and then you square them, then you naturally get the SZ term, right? So on the SZ. So that's why I've written it. So in this limit, when Jz is much larger than J perpendicular, you can of course think of setting up a perturbation in J perpendicular, right? Because that's your small parameter. So let's first ignore this. Then this is already a very interesting problem because then the ground state of this theory is when the sum of the 4 SZs is precisely 0 on each tetrahedron. Now, it turns out that there is no unique ground state for this theory. In fact, this theory was looked at by several people, including Linus Pauling and others. So the ground states satisfy the property which is known as 2 in, 2 out. So you go to each tetrahedron and you can place 2 spins as -1 and 2 spins as +1, and there are several different ways of doing it. A simple way of seeing that is if you just focus on this picture where these blacks are maybe SZ equal to +1 and these whites are SZ equal to -1, all you need to do is search for a loop like this, which alternates between plus and -1 and is a closed loop. Such a closed loop, you can just flip all the spins together. And if you flip all the spins together, you will see that you're still in the ground state manifold. And this is just the smallest possible loop that I have drawn here. In principle, these loops can even be system span and everything in between. Okay, so that's quite interesting. So it's a theory of loops at the classical level. Okay, now you turn on this quantum fluctuation, and then of course the way to think about it is that you just see what the lowest order non-trivial effective Hamiltonian that you get. So you can do this degenerate perturbation exercise. So the first thing is that this effective Hamiltonian, of course, lives in this constrained Hilbert space now. That's the first point. So what is the constraint on this Hilbert space? That whatever state you take, if you go to a tetrahedron and you sum up the 4 spins on the tetrahedron, rather the SZ component of the 4 spins on the tetrahedron, it should sum up to 0. So you cannot independently flip spins, right? So it's a constrained Hilbert space.
And if you start with one substate and then apply your new rules,
exactly. So this is actually an ergodic theory in that sense, right? So these loops give you a natural path to connect all states. Okay, good. Now, when you do this degenerate perturbation theory, then you land up with a complicated looking term like this, but this term is actually very simple. All that is doing is like a benzene kind of a term. It's making a loop of one polarity or handedness go to the loop of the other handedness, right? So it's the most local quantum dynamics that you can write in this constraint Hilbert space, right? And it's not terribly hard to see that this is also an exact U1 lattice gauge theory in disguise. So it has its own Gauss's law and everything. It's literally a U1 gauge theory. Okay. Now this gauge theory is very interesting. So this is the, of course, the full theory. Oh, anyway, I'll ignore that message, whatever that means. So the full theory is not a constraint theory, it's not a gauge theory, but the low energy theory is. And then if you look at the excitations at low energy, which control the low temperature physics of these materials, which are called quantum spinize, by the way, then there are the usual photon excitations here. But now there's an interesting detail here. When you do this mapping, you realize that this gauge theory is actually a compact U1 gauge theory. So then there are two kinds of monopoles here, a magnetic monopole and an electric monopole.
Yeah. I can't see why, even roughly why it's U1.
Oh, okay. Let me roughly write.
Just very fine.
Yeah. So, okay. So, of course, if you look at this original theory, this has some SZ conservation, right? But if you go to this subspace, this constrained Hilbert space, then actually you see that your Hamiltonian has a much bigger invariance. You can just do, okay, maybe I'll write more. Yeah, that's much easier for me. So you can just do some spin rotation like this, taking any one tetrahedron. So there are literally, so basically I'm just doing this on some chosen tetrahedron. But this symmetry operation, this is some spin rotation of four spins. This symmetry operation actually leaves your carry in this subspace, right? So it has a much bigger symmetry. And then this alpha is an angle, so it's like that's it.
U1 had its origin in Z rotations of the space.
Exactly.
And you become local.
Exactly. That's it. Right. But the fun thing here is that there are, because it's a compact gauge theory, there are both types of monopoles.
And U1 because you broke the SU2 to U1 by mistake.
Okay. Good. Where was I? Yeah. So now you see, this is a U1 theory, but it's completely emergent. So it can have properties which are quite disconnected to the real U1 that we encounter in nature, which gives us light and stuff like that. For example, I forgot to give that reference here. There has been a recent numerical work which tries to estimate the fine structure constant of this theory. It's quite hard because it's a difficult theory to solve, so they do it on the computer. And they seem to estimate that the fine structure constant is basically 1 by 10 and not 1 by 127. But that can happen because there's an emergent thing. So it can happen.
But the reason that it was compact was that it was embedded inside an institute.
Yeah, exactly. Yeah. Good. There's another very small but important point. Well, okay, these two words don't go together, but okay. Depending on your point of view. Okay. So you see, these kinds of theories also have something called a sign problem for people who love doing Monte Carlo, and I'm certainly one of them.
Extremely nice.
Yes, go on.
There is a massless liquid.
How do you know that? Oh, okay. So there's one way to actually show that nicely here. So if you take this theory, you can show that in this theory, there are some winding loops, which are some system spanning loops. And these guys are massless in some. So really what happens is you can add small perturbations to this theory and nothing will destroy those winding loops. So that's the topological protection. And in another way, you can argue that that leads to this masslessness. People say that, okay, this is gauge invariance, but I like this topological way of thinking about it better. Okay, right.
Anyway, not sufficient.
Exactly. That's why I talked about this winding loops. That's a better way of thinking. Okay. Where was I? Anyway, it's okay if I don't finish whatever I have on my slides. It's perfectly fine. So, what was the important? Yeah. So the important point is that this full theory has a sign problem. But if you look at this effective theory, which is really the theory which is controlling the low energy physics, there is some local unitary transformation of spins that you can do on certain subset of sites, which changes this J into minus J. And that removes the sign problem. And actually, that's very crucial in even allowing things like quantum Monte Carlo, which were in the end crucial in establishing this U1 thing here, because it's really hard to solve this theory completely analytically. And there are many hand-wavy statements here.
So,
yeah.
Trying to connect between the pi structure and constant thing. So it's in one field. What is the definition of pi structure?
Oh, I see.
You don't know the charge versus the constant.
Okay, so I said that there's some paper which unfortunately I forgot to quote here. So what they did was, so okay, I'll go there. So suppose you define this theory on some torus. Okay, one way of calculating the fine structure constant in such theories is you actually create a plus and a minus charge somewhere, right? And then you would do this. So you create them and then you think of annihilating them. That introduces a flux line in your theory, like a winding thing. That increases the energy of the theory a bit. You can calculate that energy difference, and from that you can extract. Good. Anyway, so you see constrained Hilbert spaces are interesting and they often arise in many situations. First, as low energy effective theories of condensed matter problems. Second, in gauge theories themselves, because gauge theories always have constrained Hilbert spaces, because there's always a Gauss problem.
Arnab,
Yes.
quick question from Zoom.
Yes.
If one just estimates, if one just fits the correlators of the theory, the electric correlators, say, to the effective theory, which is just E square minus B square, E square
Yes.
plus B square in Euclidean,
Yes.
I need some fitting parameters, right?
Yes.
And I determine those. Is that not equivalent to knowing what the fine structure constant is?
Actually, I don't know, because to estimate the fine structure constant, you need some matter fields also. If you just stay in E square plus B square, it's like you're just probing the photon mode, maybe. So I'm not sure. So because, okay, I drew that on the board.
So I can get the velocity of light that way.
But
right?
I don't
so
think
that is what I can get, but I can't get, I see.
Yeah.
You need to make a fake hydrogen atom and look at its radius, Bohr radius or something. Okay.
Anyway, unfortunately, you cannot see what I'm drawing on the board. So anyway, yeah, sorry. But I can tell you.
Actually, I could see a bit of it, but it's okay.
Oh, okay. Yeah, so that's the point, Kedar, right? So you need to somehow sort of make a plus and a minus charge and just wind them around. That introduces a flux line, and then you can estimate the fine structure. Okay, good. So now, there was this very interesting experiment by several people in the Misha Lukin lab. And they were trying to understand thermalization of certain constrained models. Okay, and then they came in with a big surprise. So maybe you've already heard of it recently, but I'll anyway zip through it. So basically, the point is these guys somehow heroically at that time produced almost isolated system or a quantum simulator of 51 qubits. So that's a really large Hilbert space, if you think about it, 2 raised to the power 51. Okay, and there, what these people expected was if they start with certain simple initial states and let the system go, then according to the schematic that I drew before, after some order 1 time, it'll just relax to the thermal answer. Right, that was the expectation, and in fact, that's what they found in most of the initial states that they started the experiment. In fact, that's how they were confident that the experiment is right. Okay, so but there was a big surprise. Certain initial conditions did not do that. In fact, it showed some very non-trivial block oscillations in the local problems. Now, as we know from quantum mechanics, block oscillations are properties of few spin systems, right? Because there are only a few degrees of freedom, like few energy levels, and then of course your cosines and sines, they can take over and you see nice oscillations, right? But here the Hilbert space is 2 raised to the power, right? So it's very hard to imagine how these block oscillations took place. So in a bit more detail, their system was one which is made of something called Rydberg atoms. So for this talk's sake, basically you can just imagine that it's like a 2-level object at each side. There's something called a Rydberg excitation and there's something called a Rydberg vacuum. Okay, so you can say a Rydberg excitation is like a spin polarized in the up direction. Rydberg vacuum is like a spin polarized in the down direction. Okay, and therefore it's again like an effective spin half theory. Okay, what they saw was if they in particular started with the Rydberg vacuum state. So it's all, sorry, sometimes I interchange +1, -1 with 1 and 0. I'm sorry. So, okay, so if they start with all the atoms in the Rydberg vacuum, then this state, when they let it go, when it like evolves unitarily, it just relaxes very quickly to whatever it should relax to. However, when they start with 1, 0, 1, 0, 1, 0, which is like a nail state, right? Because it breaks some symmetry. Right? So if they start with this alternate pattern of Rydberg excitation, vacuum, and so on, then very interestingly, there are these kinds of oscillations. But this is not an experiment, the right-hand plot. This is an actual like exact diagonalization study. What they see is that this state sort of, after a certain amount of time, seems to go to its partner 0, 1, 0, 1, 0, 1. And then after some time, it goes to 1, 0, 1, 0, 1, 0. So there are many body revivals, but that's very unusual, as I said. So this was a big surprise for the community, and it led to several theoretical investigations.
So,
yeah.
Presumably, in experiments, in the end, there is a decay.
Of course.
So, is it clear that that scale is not order 1 for this?
No, it is clear in their experiments and from their analysis that the oscillation time scale is reasonably small. Yeah, exactly. Is reasonably small so that at least they can catch the first few many body oscillations. So they are confident that there are these many body oscillations. You see what I'm trying to say? You're indeed correct. After that, it realizes that, oh, it's after all an open system, and yeah, then some other physics takes over.
No, but normally you would worry about this as a unique, interesting thing if the time scale of that decay is much larger than what you would expect in, let's say, order 1 calculation, right?
Oh, yeah, I understand what you're saying. So when you look at this 0, 0, 0, yeah, when you look at this state, you can see that the time scale where this state decays is much. So that's the answer to your question.
That sets the time.
Okay, that sets the time scale.
What's size, system size?
51 qubits. In fact, then some other group later.
Exact diagonals.
Oh, I have forgotten that, but let's see. It's certainly less than
51.
It's certainly less than 51. That's for sure. Who said that? Somebody said that. Yeah, it's less than 51. Otherwise, I would have been super happy. But anyway, it's less than 28, but it's more than 20. Yeah. So anyway, yeah. Whoever is saying this from the audience did not write the code, but anyway. I mean, in the sense that did not write this code. Yeah. Okay, sorry, you have to endure some handwritten slides now. So you can imagine what's the minimal model to understand this experiment. It's a very interesting minimal model. Looks deceptively simple, but as I discussed, it has many interesting properties, including some which we totally don't understand. So maybe some of you will think more about that. Okay, so I already said that this is a spin half degree of freedom locally. That part is clear. The second thing, which is very important, is, as I said, in the experiments, there's something called a strong Rydberg blockade. So what that means is, if two sides are near each other, let's say nearest neighbors, then if one guy has a Rydberg excitation and another also has a Rydberg excitation, then the system has to pay a huge energy cost. Okay, so that's called Rydberg blockade. So if you're a theorist, then you want to just model that by saying that if you just look at nearest neighbors on this 1D lattice of spin half degrees of freedom, then you allow two consecutive sides to have a Rydberg vacuum like this, or one guy can be in an excited state, but you completely disallow these configurations, right? So that's your constraint. So that's a constraint Hilbert space, right? So these three things are allowed locally, but this thing is completely disallowed. Okay, good. Now, let's again think of what's the simplest quantum dynamics or the most local quantum dynamics which will allow you to stay in this Hilbert space. That's the question, right? I mean, that's how you can minimally construct like simple local theories to describe the thing. So, oh, I didn't write it here, but okay. So, so the simplest thing which does this is a sigma x operator. So sigma x would just flip a like a filled symbol to a unfilled symbol and vice versa. Okay, but basically there is another restriction here. So, so if you just do it randomly, suppose this is unfilled, and I want to add the sigma x operator here, then of course what you get is this. But this is disallowed because these two guys are next to each other, right? So the only time that the sigma x operator can act is basically if you have this. So these two guys are unfilled, and then you can add the sigma x operator here. Then this is also okay, and this is also. So that's why this model is called the PXP model, because this is just a sigma x, so that's an x, and you have a projector P, and you have a. So that's the PXP. So of course, if you just had the sigma x, it would be a truly non-interacting theory. But because you have these projectors, then it becomes strongly interacting. Okay. And yeah, okay, you can do this counting of number of states here. And one signature of a problem with a constrained Hilbert space is that unlike problems with unconstrained Hilbert spaces, where the dimension is often a simple number raised to the power of number of degrees of freedom, here these numbers are non-trivial. But yeah, that's because certain states are not allowed, and you can compute using transfer matrices. Okay. Oh, so here I have already written down how this thing works. I have already explained the logic to you. So this is how the Hamiltonian looks like. So as I said, this is the PXP Hamiltonian, right? So you see there are these two projectors. These projectors are nothing but ensuring that if you want to have this dynamics, this spin is a downspin, this spin is a downspin, right? So these projectors are simply this, right? These projectors are just this. Right? So you have this times the sigma x times this again. And if you just expand out the entire thing, that's an interacting theory, right? Good.
And the number of upspins is conserved as a parameter.
No, it's not. It's not. The number of spins, upspins is not conserved.
Oh, I see.
No, it's not. Exactly.
But Arnab, sigma x can also take your upstate to 0.
Yeah,
right?
As it's doing here. So it could do that, like this, like this.
But you need the projector even then.
Even then, right? Because, see, it cannot be one way. It's after all a unitary dynamics. So if some amplitude is there this way, it has to be there this way as well, right? So if you think about it, you need the projector in both cases. Okay, good. So, okay, right.
And you are completely projecting it out. You are not saying that, this two excitation
Are high. No,
so that I can have
I'm completely, yeah.
I'm going
Correct. Of course, in reality, in the experiment, it's a high number.
Yeah, so you can do a virtual, so you
Exactly. But in the theoretical modeling, you're completely projecting. Yeah. But that turns out to be sufficient to at least mimic some of the things in the experiment. So it's a reasonable thing. Okay, so soon after that Lukin et al. Paper was published, there were these two really nice papers, one in Nature Physics and one in PhysRev. Normally one shouldn't spend time reading Nature Physics papers, but this is a particularly good exception to that rule. Okay, so yeah. So basically, again, these are exact diagonalization data. So in the first thing, they measure some local correlator. Basically, that Z1 is just the sum of the sigma Z operators normalized by the number of sites. It's just this object. So they just look at it. And there is this interesting way of plotting this, which is called a color map. Anyway, so basically these colors indicate the density of states. So warm colors mean the density of states is very high. So most of the points are actually sticking close to the thermal answer, as ETH would predict. You would say, oh, but there are outliers. But if you increase the system size, these outliers would shrink. That's the point, okay? But there's a finite theory. So of course there would be outliers. I made this statement earlier that ETH is a statistical thing, right? So you need to, yeah, okay. Good. So, however, there's certain important things which get highlighted when you go to the other plot. So suppose you take all your eigenstates and you remember this nail state which gave you anomalous oscillations, this up, down, nail state. Suppose you take the overlap of these states with that particular nail state, and here you just plot that as a function of energy. But a high energy state is like a completely random state in Hilbert space. So it would have an extremely small overlap with this nail state, right? That's the expectation. Okay. So that is certainly true, but you see that there are these interesting, very interesting tower-like structures. It's larger than the typical overlap. This order of magnitude. Okay, this is a log scale. Okay. So it seems that there's certainly something peculiar happening. So basically, to cut a long story short, actually you can just see it here. So if you increase the, okay, first thing you see is that these towers seem to be equidistant in energy. That's something you can immediately see. Secondly, if you increase your system size a bit, you will see that the number of these towers increases and they seem to grow extensively in number. So if you double your system size, the number of towers would double. Okay. So then that reminds one of, okay, you can think of several problems in quantum mechanics then. One simple problem is that of a harmonic oscillator because you want equidistant levels. But that won't explain why the number of these towers is increasing as order L. So the other natural description, simple description, which gives you this is, suppose you think of a giant spin in a magnetic field, that magnetic field splits up the levels. And if the length of the spin is somehow in proportion to the system size, then you'll again get this phenomenology. But these are just words, right? So I'm somehow saying that this picture reminds one of several. Why do I say several? Because in each tower there are several states. So this picture reminds one of several giant SU2 spins somehow protected in this Hilbert space, even though this is a completely ergodic theory. How does one know this is a completely ergodic theory? Because these people also did something which is known as level spacing statistics. And this level spacing statistics turned out to be Wigner-Dyson rather than Poisson. So there was clear indication of level reduction. Okay. But yeah. So where is this? Where are these giant SU2 spins? These must be something emerging. Okay. So let's see. Maybe I'll just skip these slides and give you an intuitive picture if I can. Anyway, there's some algebra which says that there is a way. I'll just say it in words rather. Okay. Okay. So there are these towers, and these towers have some states which are most anomalous in the sense that they have the highest overlap with Z2. And then there are things which are slightly down, but these are also anomalous. So the way of thinking about these guys is through an approximation called the forward scattering approximation, which is roughly this. You remember there was a Z2, there was a Z2 state which was basically in the spin language up, down, up, down, up, down. And there was a Z2 bar state, which was down, up, down, up, down. So imagine splitting your Hamiltonian in two parts, H plus plus H minus, and somehow H plus does the operation of taking Z2 always forward in your Hilbert space towards Z2 bar. I'm sorry, I'm being a bit schematic. And H minus takes Z2 bar backward towards Z2. So basically, these guys mimic ladder operators because ladder operators are also one-way operators, right? Now, okay, I do this decomposition. With this decomposition, you can actually show that actually this picture of an embedded spin in the Hilbert space is correct if you think of a maximally upspin as the Z2 guy and a maximally downspin as a Z2 bar guy. Okay? And then basically the effective Hamiltonian is literally some Sx, okay? Sx being the full spin, okay? But this picture is only true if you start with a Z2 or a Z2 bar. It's not true for all states because after all, it's an interacting theory. So somehow, rather miraculously, in this theory, there emerges a patch. So it's an emergent property. I mean, it's not obvious from some global symmetry of the theory. There emerges a patch which has some extremely simple description. The description is really this. Where this Sx is some big spin, okay? And this rest of it is extremely complicated, okay? But by the way, the most intriguing thing about this theory is this picture is only approximate because there are tiny numbers here. Okay? So basically, this theory is somehow perturbatively close to some idealized theory where you could mathematically do this implementation. But nobody knows that idealized theory. So that's puzzle number one. The puzzle number two is that only explains the picture for these maximal up thing being Z2 and maximal down thing being Z2 bar. There are several other outliers here. You can ask me where do they come from? So it's actually very interesting. There are these two recent papers which make a very interesting suggestion. So they say that we can think of a Gutzwiller type picture for these scars. So I'll just give you the picture. So the picture is the following. So what is this Gutzwiller thing? So, I mean, for example, for strongly correlated electrons, let's say you're thinking of a Hubbard model with a large U, which basically sort of disfavors double occupancy at nearest neighbors or something. One way to think about this very complicated problem is you totally ignore the U term, then it's just a Fermi sea, and then you take the Fermi sea, and then you hit it with a projection operator, which enforces this local constraints, right? And then that resulting wave function is actually an extremely complicated wave function, and does describe some strongly interacting correlated physics in metals very well. Okay. So here, what is the recipe? So I'll just explain it in words, and hopefully you broadly see the picture. So remember that we had this Ising chain, and there was this local constraint. So let me artificially club the sides into pairs of two, like I have done in these red ovals. I'm just doing it artificially. Okay. So inside each block, I can think of an effective spin 1 degree of freedom. Why? Because if I just do a state counting, either you can have two downspins, as I have indicated here, or you can have one downspin and one upspin, or you can have one upspin and one downspin. You cannot have two upspins. So you can effectively think of a spin 1 degree. So let's say you enlarge your Hilbert space and you go to the spin 1 description. But that's not the correct description because suppose this block has this degree of freedom, right, which is this down up, and this block has that degree of freedom, which is this up down. Then notice that that would mean that this is up and this is up, but that is not allowed. So you need a projection operator, right? So you need projection operators everywhere. So it's reminding you of Gutzwiller again, right? So you go to a bigger Hilbert space, then you write a simple state, and then you have to project that. So what is the simple state that I write? So it's really interesting. So in terms of these spin 1 variables, if you rewrite the PXP Hamiltonian, there pops out a term like this, which reminds you of a giant spin, which I was doing there. But of course, there are other more complicated terms, which are in no way perturbatively small. Okay, so but it just looks like this. Then the idea is that you have these n by 2 spin 1 degrees of freedom because I have coupled them like this, and given n by 2 spin once, there are ways of connecting like constructing a maximal spin state, n by 2, right? You construct that state, right? And then you do this projection operator. And you see that that describes those top stars. But why stop at n by 2? You could have done n by 2 minus 1, right? That gives you the, that gives you the lower tower of stars. Then you do n by 2 minus 2, that gives you the still lower tower of stars. So you see, there are actually these large number of giant SU2s embedded together, and they somehow seem to arise in this picture in a slightly more natural way. But I think you would all agree that this is still not what one would call an exact understanding, but I think this is certainly in the right direction. So there's already an intriguing question here, that why this is.
Okay. So what was the thinking there starting with this? So it's just that these three states gave the idea of an effective spin.
Exactly, right. And so you have, see, this is the point. This is the point here. Let's go to this picture again. Whatever you do to one SU2, the other SU2s are not independent, right? Because these towers are coming together. So if there is a good picture, it should explain the multitudes of those things. So at least this picture is, I think, on the right track. Right. So good. So that's already an interesting thing here. But there's something even more interesting. You might say that, oh, okay, these cars are, of course, very interesting, but they are subdominant compared to the rest of the Hilbert space, right? Their numbers are extensive, but the full Hilbert space is exponentially large. So they are subdominant. But there was actually a bigger surprise in store. And what was that surprise? So let's just discuss that. Yeah, let's discuss that. So this middle graph is just showing you what I said in words before. These guys looked at the level statistics of the PXP model, and it showed level repulsion and not Poissonian statistics, which is indicated by this dotted. That's all this is supposed to be. Okay, now let me go over this slide slowly. So if you just stare at level statistics, you would say that the PXP model is a chaotic theory, is a non-integrable quantum theory. Okay. Then you ask, what are the conserved quantities in this PXP chain? The only conserved quantity here is energy, because things like spin are not conserved here. So energy is the conserved quantity. So you can think of studying energy transport. It's like saying you have some state, you dump a certain lump of energy somewhere, and you just watch how it relaxes. Right? So that is energy transport. And because it's a conserved quantity, it makes sense to study that. Okay. So what do you normally expect for a chaotic theory? So for example, if you take a normal Ising model in 1D, and it has both transverse and longitudinal fields, so that it's not integrable like a transverse field Ising model, it's completely non-integrable. And there you study the energy transport, just like I said, you will see that the spread of energy is described by a square root time behavior in time. The spread is square root time. But square root time just happens because of diffusion. So basically what it's telling you is that the energy transport is diffused. Okay, that's a reasonably intuitive statement. Okay. But in this theory, in this PXP chain, this recent paper in 2023 did some rather heroic numerics. So forget about the technique. The important thing is they could do a system of size 1024 sites, and they could sort of evolve it till rather large time scales of 300 or so, where the natural unit of time is 1. Okay, so it's a pretty impressive calculation. So in this calculation, what they studied was they took an infinite temperature density matrix and studied the energy, local energy autocorrelation in infinity. So they took infinite temperature because they wanted to see some transport characteristics, which are characteristics of the full Hilbert space.
So they took the density matrix and they did not take, just individual states with equal probability.
No, they literally took a density matrix. And they perturbed it, and yeah, and they measured local energy autocorrelation functions, connected autocorrelation. That's right. The relaxation of that connected autocorrelation functions gives you something which is known as a dynamical exponent, Z. So just to be on the same page, without going into too much detail, suppose we just think of a particle which is doing some complicated motion. Okay, then basically, where is the particle? Yeah. Then, if you look at that particle and see its spread as a function of time, And for that, you just calculate R square expectation value, where R is the coordinate of the particle. Then basically, this thing goes as P raised to the power 2 by Z. So some simple limits that we are aware of is when R square goes linearly in time, that's diffusive. Okay. When this is sort of, so this is like this straight line here. When it's going slower than that, that's subdiffusive. When it's going faster than that, particularly when 1 by Z is 1, that's ballistic. It's like free particles. Okay. Okay, so I have written that there. So now, here, what they see from the numerics, if they see this running constant, right, this running constant, and when time becomes really large, this should saturate to the correct dynamic exponent, then they see intriguingly that this 1 by Z is very far from the expected answer of half. So this is half. It's very far from that. In fact, it seems to go to 2 by 3. So for people who know, and I'll come to it in the next slide, this 2 by 3 is a very special number if you think about dynamical experiments. Okay. Of course, you cannot rule out that maybe if you wait for some really long times, maybe this will ultimately flow to half and become diffusive, which is what this plot is trying to indicate. But okay, at least till these large time scales for a rather big system, it's sufficiently different from half and sufficiently close to 2 by 3. Was there a question? Okay, good. So 1 by Z is 2 by 3.
One of the usual problems is you are trying to keep an exponent.
Correct. That's why they are doing a running exponent.
Running exponents are always a little
tricky.
tricky.
Of course. I understand.
You really need.
Yeah. So exactly. Yeah.
But okay.
Yeah. But at least, I mean, they're taking a local derivative and they're estimating. Yeah. Okay. But there is reasonable indication that this is super diffusive. That much is clear. And also within their numerics, there's reasonable indication that this is far closer to 2 by 3 than half. Half is understood, it's diffusion. 2 by 3 is something else. What is this 2 by 3? So, of course, 2 by 3 can happen due to a variety of reasons. But, yeah, I mean, obviously, right? I mean, 2 by 3. Why am I harping on 2 by 3? But 2 by 3 happens to happen in physics in a very special context, which is KPZ, Arda Parisi Zang Universality class. So I'm not an expert in KPZ, so don't ask me detailed questions. But roughly speaking, if you look at surface growths in many realistic situations, and if you look at height correlations, then basically they don't seem to follow some Gaussian fluctuations, rather they follow a different universality. So one toy problem to think about in this is this corner model of surface growth. It's a pretty cute model. So let me just explain this model to you. And if you're numerically inclined, you can quickly code it in your laptop and see this in front of your own eyes. So you just take a wedge like this, right? And you start it empty. So when it's empty, there is only one local minimum, which is indicated by this red dot. All of you agree, right? So there's also some natural grid here of points. This grid is to indicate that I just put a unit square on this. These are the degrees of freedom that I put. Okay. So now you do a stochastic process. So that is, you wait in time according to some Poisson process, so some exponential waiting time. And when your timer clicks, you put a square stochastically at the local minimum. Here, there is only one local minimum. So you just put the square here, right? Clear? Now, when you put the square here, it generates two local minima. I hope you can see it from the picture, right? This is the local minimum, this is the local maximum. But this time, this is the local. So in the next move, which is again determined by when this thing clicks, this exponential waiting time, you could have put the square either here or here. So let me choose to stochastically do it here, right? So yeah, now there is this guy and this guy. Now you can place the next thing here, right? Then you see now it becomes more and more complicated, and this local minimum is indicated, this is indicated. So you can keep doing. So that's the process that you do. This is called oh, I forgot what it's called. What is this called? It has a name, particular name, corner something. Of course, there must be corner in the name. Anyway, it's called something. Okay. But you can read this reference. That's why this reference. It's so, okay. So when you keep on simulating this process, you see this very non-trivial surface image. This surface, right? This surface. Now, if you look at the, oh, sorry, it's called corner growth mod. It's written here. Okay. So when you look at the surface and study its fluctuations, then you see that the fluctuations are of the order of e to the power 1 by 3. So that's t's time here. And if you look at the height correlations, height which are spatially separated, you see that these things decorrelate on the scale of e to the 2 by 3. So that's one simple realization of KPZ. And now you can see why numbers like 2 by 3 emerge, right? So in this PhD model, which seems completely non-integrable if you look at level statistics, if you somehow look at energy transport, it seems to be super. That's a numerical result, but at least it's a very weird numerical result.
A question from Zoom.
Yeah.
Instead of doing this very heroic numerics at this size 1024,
yeah.
Has anybody tried to look at it as a function of L, and after all, you can extract the exponent Z from finite size scaling or something as well, right?
Oh, you mean from exact diagonalization?
No, whatever numerics they did at 1024, you could do at other sizes, smaller sizes.
Yes.
And do finite size scaling. No, that's less heroic, but perhaps has more information or no?
Right. But as far as I know, they haven't done it. And if they did it, at least I don't see anything published to that effect. Yeah. Yeah, but they haven't done it as far as I know. Yeah. That's a good suggestion. Yeah. Okay, good. So now you might ask me, are there other examples of KPZ-like regimes in spin transport, in transport of other theories? It turns out that there are some other examples in the literature, but none of them are well understood, as far as I can tell.
Is there an understanding of 2 by 3?
No. The understanding of 2 by 3 here is that, okay, it's in the KPZ class, but as far as I understand, now this is really the limits of my understanding, so somebody can correct me here. Normally, you have one conserved quantity in your dynamics, right, like energy. But sometimes if you have 3 conserved quantities and these 3 conserved quantities or more have the right characteristics, you naturally fall to a different fixed point, which is the KPZ universality. So that's the end of my. Oh, the 2 by 3 corresponds to, for example, here some temporal fluctuation and.
No, I understand what we say. What does it correspond to in terms of, right? And the number means should mean something.
It specifies that universality class. Sorry, I'm not.
Around that fixed point. So here it is a high-tech correlate.
Yeah.
This now. If it was
more precisely, I think a more direct answer is here. Random walk, for example. Like, think of it here. If you dump energy in a non-integrable theory, energy is a lump and it spreads. You can watch how it's spreading, literally. I mean, of course, it's very difficult. It's a thought experiment. But if you think of this thought experiment, then basically the general expectation is that you go diffusively. But these guys see that this is already super diffusive. So this is rather non-integer. And okay, unfortunately, I cannot give you a deeper understanding of this 2 by 3 rather than just saying what I said.
So it's not related to dimensionality of the problem or
no,
degrees of freedoms and all.
Hey, is this corner model integrable by any chance or no?
Which one?
The corner one.
Oh, the corner one is an integrable stochastic process. The corner one is an integrable. Yeah. Okay. Great, Kedar, you raised that point, but let me take the question from Shiraz and then maybe I'll come.
Yeah, so I'm just trying to understand when you say universality class under what? And some sort of article?
You're going to the limits of my knowledge about KPZ. Yeah, so like stochastic random processes also have some universality classes. So I think KPZ is one universality class there, but I think maybe someone in the audience has a better answer.
Stochastic differential equation, and you have IT with only diffusive terms, then it will flow to some fixed point, and the dynamic it will flow to a fixed point.
And it may based on time.
What do you mean? You rescale the time and the space and source frame and see how it flows.
Right.
And in the KPZ, you have some additional term, which is a kind of del X non-ideal whole square. It's a minimal kind of non-trivial term or relevant for the And this term already flows into the.
So is the language of conformal field theory useful for this or?
No, that I know.
So 1+1 dimension?
No, just tell you. This is 1+1 dimension, 1+1, but
At least the simple model.
but it was scaling both x and phi.
Yeah, I don't know whether CFT works.
Not until that.
Yeah.
Otherwise.
Yeah. Sorry, Kedar, you had a question?
No, you already answered it, right? You said it's integrable, this toy model.
Oh, no. Yeah, this one is this is an integrable stochastic process, right? And I really recommend you read this paper. It's very nicely.
This is the asset model. If you look at the lab.
Yeah, correct.
So it is very-
Yeah, but yeah, it is very simple if you think of these squares. Anyway,
So,
yeah,
no, we are 515.
Oh.
No, I just think how.
maybe.
It could be.
Yeah, sure. 10 minutes could be. Anyway, I think maybe already you see that there are interesting surprises here. And of course, this is just some aspects of it. Okay, so in the remaining time, so I won't take much time. I will just breeze through the rest of it. So of course, I told you about the PXP chain, which is one constraint theory. Now, as a theorist, you always play the game of generalizing things, right? So let me just generalize the PXP model, and then I'll get this funny model, which I'll explain. And this model has some very cool properties. One cool property being that usually you cannot write any high energy eigenstate exactly in a non-integrated. In this model, you can write several of the high energy states exactly. And that's the nice thing. And then there are some other really nice things. So I'll just explain it in words and then I'll stop. Yeah. I had some other things, but that's okay. Good. So you remember the Hilbert space constraint that we had? The Hilbert space constraint that we had was that 0, 0 is allowed in neighbors, 1, 0 is allowed, 0, 1 is allowed, but 1, 1 is not allowed. Okay. So now the most local dynamics is this, as I already alluded to. Now you can think of slightly more non-local dynamics than this, non-local in space. This is one such dynamics. If you see a 1, 0, 1, you go to 0, 1, 0 from there. And these things can again be thought of as effective spin halves because this is like a time reverse copy of this guy. Okay, so this we call Px3p because there are these 3 sigmas involved here. Okay. Now, this problem, of course, did not arise from vacuum. We were doing some other problem, and there's something called QK physics, and we were doing that. And when you do a perturbation theory there, this is the leading piece which comes about. Okay. Then actually we figured out that this leading piece itself is super interesting. Okay. So that is the history. And of course, one of the co-authors of this paper is sitting in the audience. Okay. So yeah, the other two are somewhere. Enjoy. Okay. So good. So what is the nice thing about this thing? This full theory is non-integrable. But this thing breaks up into certain pockets in Hilbert space, and some of these pockets can be solved very easily, which is rare for a non-integrable. Okay, so let me just describe it schematically. So there are these green pockets, and the size of, or blocks in Hilbert space, the size of them can be as small as 1 and as large as 2 to the power n cross 2 to the power n, where n is bounded above by L divided by 5, where L is your system size. So you can see that this block is 1 cross 1, this is 2 cross 2, this is 4 cross 4. Then it can be as large as 2 to the L by 5 cross to the L by 5. All these blocks, I can actually tell you what are the eigenvalues and what are the eigenvectors. And these are what we call bubble sectors, because these blocks have a description in terms of perfectly localized volume. By the way, this should already be surprising because I'm talking about high energy states, and high energy states typically don't have any quasi-particle. Okay. Then there's something even more surprising, which is something called secondary fragmentation. We were the first ones to point it out, but then some other people from some more well-known places used the word quantum fragmentation, and that caught on. But That's a separate issue. Okay, yeah, okay. So the point is, then there are these other fragments which are completely thermal, like this. But remarkably, you can actually, it's like peeling an onion. You can actually peel some layer of it, and that layer actually is completely orthogonal to the rest of this block, and under the action of this Hamiltonian forms a subspace of its own. So then you can solve for that subspace, whereas the rest of the thing is flawed. So what you were trying to do, what you saw approximately here, happens exactly here, right? So that's what's called secondary fragmentation. So let me just explain this terminology a bit, and then I'll just show a couple of pictures, and then I'll start. So maybe from Sanjay's talk, you already know what fragmentation is, but let me just say it in my way. So, okay, it's good to just look at this picture for that. So what is this picture saying? It's just illustrating a small system of 6 spins on a ring, periodic boundary condition. And on the top, you just generate a Fock space graph, and I'll explain what that means, using the PXP Hamiltonian. And on the bottom, you do it using the PX3P Hamiltonian. So what is that? So, there are these states here, 18 states, which I've labeled explicitly here. Now you have your Hamiltonian. You can just think of the terms of your Hamiltonian as some sort of a Markov process, right? You're after all just flipping a spin. So you have a Fock state, you just flip a spin, and you go to another Fock state, you keep doing that, right? Suppose you keep doing that, there's no quantum mechanics yet. Then you generate a Fock space graph. So this is the Fock space graph for the PXP theory. The first thing to note here is every vertex here is connected to every other vertex. It may be a complicated path, but it is connected nonetheless. That's the meaning of an ergodic graph. In the other theory, you see it splits up into fragment space. So there is one thing here like this, which is on its own. So that's the vacuum state. So if you take the state 0, 0, 0, 0, 0, hit this PX3P Hamiltonian on it, it just annihilates that. So it's just on its own. It's not connected to any other state under this Hamilton. Then there are these fragments which are 2 cross 2. Then there are these fragments, this fragment which is 1, 2, 3, 4, 5 cross 5. But this is again a purely classical effect. I don't need quantum mechanics to think about that. But this secondary fragmentation is actually beyond it. You actually need to construct amplitudes in the correct way so that these vectors, these finite number of vectors, even though this thing is infinite in a big system size, are actually orthogonal to the rest of the vectors here, and they form a closed subspace. That requires these quantum amplitudes in a very crucial. That's why it's called secondary fragmentation, but in hindsight, maybe we should have called it quantum fragmentation.
Is this phenomenon stable to the values of the couplings in front of the PXMP at different places in the lattice? Like, can I put disorder in the couple? So you have some coefficient.
Oh, no. This secondary fragmentation is more fragile, right? So
okay.
Yeah, it's more fragile because it needs these amplitudes in a very delicate way. That's correct. Yeah.
Right.
Yeah.
So this is not what Sanjay was talking about.
I don't know what he was talking about.
He was talking about things where you have a family of Hamiltonian which are.
Yeah, that's why I asked this question. I think Sanjay's is the other example that Arnab is contrasting his example with.
Right.
And be able to change this locally value.
Yeah. Okay. But probably he introduced the word fragmentation. That's what I said. Maybe.
No, I was just trying to see if there's any connection.
So you see, this thing has some very cool things, and I'll just show you some pictures and stuff. First thing is that these bubble sectors have completely localized quasi-particles, which I'll describe. Then, generally, you think of bands in low energy condensed matter, right? But I'll show you that here, both flat bands and dispersing bands arise at arbitrarily high energy, which is the cool thing. And the nice thing here is I can write it exactly analytically, right? Which I was quite happy to do.
Richard, these are essentially classical configurations in
No, these are classical configurations, but when you turn on the HEX3, then it becomes a completely quantum problem. For example, just to show you that it's a completely ergodic theory. Sorry, I'm going the other way. Sorry, I haven't. You should not have seen all this, but it's okay. Here, if you look at the half-chain entanglement entropy of all these eigenstates, this is the half-chain entanglement entropy. I don't know, there's a hand here, but okay, anyways. This is the half-chain entanglement entropy here, and for the EXP theory, and this is the thing for this theory. Now you see, if you look at the typical states, you remember it's a color map. If you see the typical states, you see that the half-chain entanglements here and here are exactly the same. That's the meaning of the fact that even this theory is ergodic. You see, right? Okay. But let me just rush. So let me just show you this picture and maybe I'll stop then. Right. So this is the full spectrum of the theory from exact idealization for an L equal to 18 system size, which I have resolved using momentum, right? And so there are only a finite number of momenta for this system size. So you can just see the data plotted like this. And again, this color map indicates density of states. Right? So wherever this color map is high, it's a high density state. So you see, I have drawn two flat bands here. Like you can see these flat lines and two dispersive bands here. So these kinds of band descriptions emerge even at extremely high energy. And you can completely analytically understand them.
So the bands are contours of equal density of space. I get a color map, I understand. So what am I joining with?
Oh, okay. Here I literally know the states, that's why I'm joining them.
Yeah.
But only these states have band description in terms of hopping quasi-particles. Exactly. You couldn't have stared at this picture and guessed this.
So
Right.
yeah.
Right. But if you look at a neighboring state, that does not have a band description. But it's quite incredible that high energy states, at least a class of them, have band descriptions. Anyway, you can write analytic expressions and figure out why there are bands. Let me not go there.
So one of the only things that people did with PHP or similar things was what we could call single mode approximation, which finally used for EVM.
This is disconnected.
This is connected to
This is
disconnected.
Disconnected. Yeah. We can talk about that. This is disconnected. This is a completely different phenomenon. Yeah. So anyway, this can be mapped to some gauge theory. And one fun thing here is that maybe some of you already know, if you have charge and dipole conservation in a gauge theory, then there are some things called fractons. I'm really sorry, I'm rushing through some slides now. But yeah, anyway. Right. If you just have charge conservation, you can move free charges around. But if you have both the conservations, you cannot move free charges around. This theory, when you map it to again, a peculiar U1 gauge theory, you can easily show that this theory does not have sorry, what am I doing? I'm sorry, I'm just going back and forth. You can easily show that, where is that thing? Okay, you can show that here. You can show that this theory does not have a dipole conservation. In the sense that suppose I create a dipole like this, then I can create excitations through which I can just stretch this dipole. So clearly it doesn't have dipole. It only has charge conservation. However, if you look at those anomalous states that I was talking about, those sectors have an emergent fracton motion. For example, if you think of the simplest dispersing bands, which I haven't explained to you, it's almost like thinking of a length 3 dipole supplemented by 2 charge neutral objects, and these guys float on them. So that's an emergent fracton, right? So, and then if you go to some more complicated secondary fragmentation, even larger neutral patterns emerge, which become mono. So here, these things are completely emergent. They're not there in the specification of the Hamilton. Okay. So anyway, there's lots of fun you can do. You can play the same game in 2D, and there's lots of fun there, but I don't have time to explain it. So maybe I'll just show this slide, and hopefully I've already convinced you that there are several interesting things to think about in the dynamics of kinetically constrained models. Of course, some things we understand, but there are many, many things we don't understand. So of course, it means that we deeper understand this. Thank you.
questions? That's all questions. Yeah.
You said that in the PH3P model, you have the I and the exact state.
Some of them we can write down.
So can you just show how they look and are they something like the ATL?
No, they're not. They're different. Well, okay. I did want to torture you, but okay. So let me show you one example analytically. Let me show you the simplest example analytically. Sorry, I'm still not very used to this. Okay, yeah. So these are what are called the bubble sector. So imagine a vacuum. This vacuum is the all down state. In this vacuum of all down states, suppose you put an island, where this island can either have up, down, or down, down. Okay. You can show that this island is completely immobile on the action of the hammer. This is a simple thing to prove. Now, just from this fact, you know that if you put another island here, that will also be completely localized because it's a local Hamiltonian. Now, the interesting bit is you then ask the question, how close can these two islands be so that they stay local? It turns out, you can prove this again reasonably easily, that the minimum spacing between them is 2 sides. Okay, so yeah, so you can build lots of these localized islands. Now, in each of these localized islands, the dynamics is very simple. This classical state x1 goes to x2 and x2 goes to x1. So it's like a sigma x operation. Right? So it gives you all kinds of integer items. Because if you take this Hamiltonian here, it just has integer solutions. So, but these are not the only non-zero integer solutions in this theory. In fact, we don't understand most of the non-zero integer solutions in this theory. In fact, just because I made the statement, if you have a completely chaotic theory, the fact that you get non-zero integer solutions already means that those states are analogous. Because
Arnab, in the example you have displayed here, the secondary thing you talked about is the fully connected graph, and the conventional classical fragmentation is the one with disconnected bits.
Exactly.
Is that the general statement, or that's just in this example? I mean, is secondary the same thing as saying Hilbert space graph is fully connected, but you have these states?
Yeah, exactly. So I think that's a reasonably general statement. Yeah, I think now there's a consensus in the community that this is the general statement.
So if you find these scars in a completely or fragments in spite of having a fully connected Hilbert space graph, then that's secondary fragmentation.
Yeah.
Is that what you say?
Yeah, that's what I'm trying to say. Yeah.
Okay.
Sure. So coming back to the first part of your talk, where you have this little corner out there. Does that ever happen in a situation where you have a continuum field theory kind of approximation to the dynamic, which is some of that in this theory?
Oh, I see. So you're trying to ask whether in some ways lattice effects are important. Yeah. My intuition is that lattice effects are important here, but I have no way of proving or disproving my statement. It's just an intuition.
All the examples we know that is effect are.
Yeah. But some people have tried to start with continuum theories and get scars from there. But okay, I haven't understood those papers sufficiently well to say that the phenomenology of this goes to that in some smooth way.
Can you give an example of that? Or in a continuum theory, are there examples of scars?
Okay, there's one guy who was at some point a postdoc in Harvard. His name escapes me, but I can find the reference later. And yeah, so okay, I think there are examples of that.
Okay.
Yeah.
Can I ask one last question?
Yeah.
Are there examples of this secondary fragmentation which is stable to variations in the coupling constants like disorder?
Really interesting. Unfortunately, I don't know of any. Yeah.
Okay, thanks.
Okay, so if there are no more questions, let's thank Arnab for everything.